Next speaker is Yaron. Let's speak on Unraveling Turbulence, Modern Viewpoints, and Unsolved.
Thanks, Spenta. Okay, good morning. It's a great pleasure for me to be here celebrating Hiroshi's birthday. And let me tell you a little bit about my history with Hiroshi. So the first time I met Hiroshi was actually, we collaborated, was after my long military service. It was short after the military service. And we wrote this paper on Calabria, on Librons and Calabria spaces, A-brains and B-brains, together with Zheng Yin, who was Hiroshi's student. And for me, it was a unique experience after this long military research, because military research was in 4 dimensions. And as it turned out later, since that paper, whenever I had to cross borders, I had this pass in the border control, and they would ask me, what is your profession? What is your research about? I would always tell them, I'm working in higher dimensions. It worked actually pretty well, except in one time that they freaked out because I told them that I work in 11 dimensions. I think they didn't like M theory. Perhaps they were on the loop gravity side. I don't know. Since then, we have been writing actually large number of papers together with many people in the audience here, like Chaba and Yan, and also this review with Juan, who, as far as I understand, some of the students call the Bible. So thank you for all these years of collaboration and friendship. And Jan yesterday proposed a wonderful matrix model description of Hiroshi. So I thought that by Occam's razor, maybe I should offer a simple model. And I look at only one piece of empirical data that was discussed by the speakers here, which are the facts that Hiroshi is a director at the IPMU in Japan. He's a director of the Book Institute here in California. He's also the chair of the board of trustees in Aspen. He's in many international organizing committees. So my take from this is that he can be in many places at the same time. So congratulations, Hiroshi, you are an officially quantum particle. Actually, this is moving. It's not moving.
Okay. Don't worry, I found the trick.
You found the trick?
Yes.
Now
it works.
Now it moved. So you are officially a quantum particle. Actually, it's getting better than that. Last week, I was in a workshop on many word interpretation. Don't ask me why. And but according to them, there are many copies of you as a quantum particle. Many things have been said about Hiroshi's skills of course, in science and in administration. So I want to offer 2 comments, what I found unique about his administrative skills. One time we had a discussion, I think it was in a cafeteria of Simon's Center, about administration. And I just gave my usual mantra that if you want to be an effective as an administrator, you need 3 resources: money, budget. You need people, positions, and you need real estate. So Hiroshi looked at me, he was smiling, maybe even laughing, and he said, I don't have any of this in Aspen. So still, you are very effective without all these resources. The other thing that I noticed, which is unique, is so I have to explain to you the difference between science and administration. In science, you try to be very accurate, very precise, get to the point. In administration, it works differently. You try to be vague, you create friction. Any one of you who try to get money or positions from the dean or the provost knows that very well. But Hiroshi actually works in a different way. His science and his administration work exactly in the same way. So my recommendation is don't try to learn new tricks now. It works very well. And lastly, just to end my what I would like to say about Hiroshi, let me tell you a story. Actually, it's a true story, not about you. A few weeks ago, I met a friend of mine, and she is a scientist in medical school, and she works for many years on Alzheimer's disease. So I asked her, Ilana, 50 years you're working on Alzheimer's disease, give me some piece of advice how to avoid it. And she told me, Yaron, I have only one advice to you. Keep working hard. So Hiroshi, my wish for you is that you will keep working like 5 people. It's good for the community, but it's also good for you.
Thank you.
And let me now go from order to disorder. And so this is a problem that actually I got interested in it more than a decade ago. It's a problem of turbulence. And I will tell you what is the problem statement and 3 different directions to look at it: field theory, holography, and machine learning. Basically, I'm throwing everything that I have on this problem. There is actually one other piece of thing in information theory that I don't do, but it's maybe for another discussion. So the first scientist to actually try to understand in some way turbulence was Leonardo da Vinci, and he was trying to accurately plot the vorticities of the vortices of the Arno River turbulence. And turbo by itself is a Latin word for crowd, and turbulence originally refers to a disorderly motion of crowd. That's why you hear like turbulence in the Middle East, turbulence in the White House, etc. However, scientifically, it refers to complex and unpredictable motion of a fluid. And what is turbulence? Actually, fluid turbulence, you know it when you see it. You look at it, you know that it is. And it's an emergent complex structure from a very simple set of rules, basically Newton's second law. But mathematically, the framework to describe it at low Mach numbers, lower than the speed of sound, is the incompressible Navier-Stokes equations, which dates to 1822. And basically, these are equations for a velocity vector field. And the equations are you can formulate them like that in d equal or bigger than 2, and equal to 1 is a little bit different. And there is the nonlinear term, which is the one that creates all the structure and the mass. And there is the viscous term that plays against it. And basically, the ratio between this one and this one are playing, are the major players. P are the pressure forces, but they are actually related by constraint to V, and F, it could be an additional random force that you could. Now, as you know, one of the clay problems is just to even understand whether this set of equations have a solution, a unique solution, a well-defined solution that doesn't have finite time blow-ups, which is a problem not unrelated to sensors, cosmic censorship that we know. And there is a dimensionless important parameter in the problem introduced by Reynolds, and this is the ratio of a length scale, characteristic length scale, the velocity difference at that scales, and divided by the kinematic viscosity. And that number, when it is that's actually an empirical and numerical evidence that when it is of order of 10 to the power of 3, you see turbulent structure. And this is Reynolds, that's taken from Wikipedia, and he was doing that experiment using this pipe, and he was injecting dye, and there was a laminar flow, and then when he increased the speed, the velocity, then he got into the turbulent flow. That's how he found out that definition of the number. Now, turbulence in nature is actually all around us, and the reason is very simple, is because the viscosity, the kinematic viscosity of water is 10 to the minus 6 meters squared over second, while that of air is a little bit less because you divide by the density. But both these numbers are so small, and because they are in the denominator, whatever you do, you create this 10 to the power of 3 Reynolds number. Now, trying to understand individual solutions is very complicated because it's a very chaotic system, so it doesn't make much sense. So people decided to look at statistical turbulence, which is looking at the space of solutions and trying to understand the statistics of them. And one defines the inertial range to be a range of distance scales, R, which are much bigger than the viscous scales and much smaller than the forcing scale. And it turns out that there is a lot of numerical and experimental evidence for many years that the statistical averages in this range, they exhibit a universal structure. It's a universal structure which is shared by all fluids, air, doesn't matter how you created the turbulence. And the one thing to say about it is actually it's been never proven mathematically. So nobody has proven that mathematically starting from Navier-Stokes, you should really get scaling. So it's really an empirical and numerical evidence. And there are all kinds of fluid observables. So one typical fluid observable that people measure is velocity differences at a given a point in time, because you reach basically steady state statistics. You dot it with the vector that is the connecting these 2 points, or the transversal one. And then you calculate these structure functions. These are averages of these operators. And then they always scale like R to some power, some set of powers, xi n, and these are universal numbers. So this is a set of infinite universal numbers that they always show up and and one needs to explain them. Kolmogorov in 1941, actually it's the most embarrassing thing is that the most important actually contribution to this field was by a mathematician. But this is Kolmogorov from 1941, and he based on several assumptions about scale invariance, what we call mean field theory or dimensional analysis. At the end of the day, he concluded that all these numbers are just these rational numbers n over 3. So it's linear scaling. And typically you see in the books, when you put n equal to 2 in the Fourier transform, you see this so-called Kolmogorov scaling, which really matches nicely with the data. However, soon, several years actually after he wrote his paper, it was clear that this is not correct. And in fact, if you see his linear scaling, the fact these anomalous exponents as a function of n, they agree only at n equal to 3, that the value is 1 and that you can prove analytically, and all the rest are different. In fact, there is a little bit of a gap here that starts to increase. And this is deviation from scaling variance. And this is the thing that needs to be explained. So this is the problem statement. Of course, there is a second order problem, which is try to understand all the multi-point correlation functions. But this is defined as the problem of turbulence. Basically, get us correctly this number, this exponents, this infinite set of exponents.
What is blue curve?
What is what?
The 3 curves here.
Yes. The other one is the Burgers. So in one dimension, it's a different system that the physics is the physics of shock waves, and the exponents are basically all 1. This is called Burgers equation. And it turns out that you can ask something about, you can ask me whether there is any dimensionless expansion parameter of Navier-Stokes, and there is one. It's a number of space dimensions. So you can ask what happens when D goes to infinity. And we have sort of a conjecture that Burgers equation, it controls the D equal infinity, and I can explain why. But it's not relevant for this talk. So the task is just to find this curve or explain all these numbers. So some time ago, and during we could derive an equation that describes that curve, and that equation tells you that these exponents deviate from Kolmogorov scaling by this quadratic equation, where this is a number, is dimensionless number that depends on the number of dimensions D. It's different in D equal to 2, 3, etc. But other than that, it doesn't care about anything. And you will recognize this equation, many of you, as the KPZ equation of quantum gravity, and I will explain in a second why. And if you look at the data, so you can compare it to data in different dimensions, but show you the data in 3 dimensions. So for instance, compared to experimental data, you can just fit it. But as you see, the errors here are pretty big on the experimental data. That's one of the problems. There is no field of precision turbulence. So it's actually very difficult to verify which formula will be the correct one. The same story with the numerical one. You can calculate again this number. It's around the same number. So it fits all the possible data. It's also consistent analytically with all kinds of constraints. Now you can ask why. Why would you have random geometry in this business? And the reason you could ask me is because this is just turbulence in ordinary flat space. So who cares about random geometry? So let me remind you how Polyakov Zamolodchikov equation came about and actually how the mathematicians view it. So the way it's viewed is that if I give you a set of numbers, scaling dimensions with respect to some Euclidean measure, d mu, and I define a new random measure, which is an exponential of a Gaussian free field, it has logarithmic correlation, then the equations that the new dimensions satisfy related to the dimensions with respect to the Euclidean measure are the KPZ equations. So you can ask, where can I get any field like that in fluid dynamics? And the answer is as follows. If you go into the inertial range and you in the absence of viscosity, you can easily check that's well known that the Navier-Stokes equation has actually independent scaling symmetry of space and time. So there are two different parameters, sigma and z, and they are real numbers. But there is a flux in the system. The flux is an expectation value of this observable, and what it does, it breaks this symmetry to z equal to 2/3, so to this dynamical exponent. And this is exactly Kolmogorov scaling. But now if you view Kolmogorov scaling as spontaneous symmetry breaking, you can ask, where is the Goldstone boson? So you parameterize this observable as an expectation value times this field, and you can ask by symmetry, tell me what is the effective action for that Goldstone boson. It turns out that it's a kind of a generalization of Liouville theory. You can add the exponential, but it's not relevant here. It's like a Gaussian free field with a background charge. And these are the operators that you know very well in 2D, and their generalizations are basically these fractional Laplacians or GGMS operators. And this is the generalization of the curvature. It's called the Q curvature. It's conformally invariant of manifolds. These are interesting theories. And now if you do that, you dress all the observables of K41 theory, the ones that have this linear scaling, by this dilaton, and you just follow your nose, the same thing that was done by Kawai, Dissler, and Nizhikvolikov, Zamologikov, you will get this KPZ equation. So basically, it will tell you that the difference between your actual dimension and the midfield dimension of K41 is solved by this equation. And this is the parameter that I called calligraphic G before up to normalization. How is it determined? So if you remember in 2D, the way it was done is by asking that the total chemical charge vanishes, and therefore there was an equation that one could derive it. You can play the same game here. You can ask that things do not depend on the large scale. So when you vary things with respect to the log of the large scale, it will vanish, and that will give you an equation on the trace anomaly. So it relates this dilaton anomaly to this K41 anomaly, and you will get an equation like that. The task is to calculate this one. So this K41 theory is a non-local, non-unitary theory that gives you these dimensions which are linear, and try to calculate this object. So far, I haven't managed to get the right number. So, but if you, at this point, what you can do is you can just measure one number and then get all the others. So that's the field theory part of the story. The second part of the story is holography. So you can think about the black holes, and black holes horizon is actually very crucial because, as you know, fields they fall in, but they cannot emerge back. This allows us to introduce dissipation into Einstein's equations. And if you look at the dynamics of the horizon, so I take a planar horizon here. There is a good reason for that. It's because in asymptotically flat spaces, it's a little bit trickier than that. But if you think about the planar horizon and you perturb the black hole, the Gauss-Kodazzi equations or Einstein's equations projected on the horizon will give you exactly Navier-Stokes equations, but the normal is the velocity. And what it means is that all the information of turbulence is encoded in the extrinsic structure of this surface. So therefore, there is maybe an interesting way in which all these pieces of universal information is encoded geometrically. So I give you one example of a calculation. So suppose I take this local energy dissipation and I calculate an observable like this. It's just an integral of that over a sphere. That's a well-known observable introduced by Obuchov, who was a student of Kolmogorov in 1962. And if you calculate the expectations of this, you will get anomalous scaling. But we did this calculation at the moment only in 2D, numerically. This is a paper to appear with Sebastian Weber and Amos Yaron. And in 2D, because the expectation value of that was the one that was breaking to z equal to 2/3, the dimension should be 0. And actually, that's what you see. So the horizon does seem to capture correctly the physics, and now it's interesting to see whether you can learn something from it. Because, you know, naively you could have said that anyway, you can get everything from the boundary, so why do you care about the horizon? I think the structure of the null surface captures it in a clever way. And the last thing I wanted to tell you about is machine learning of fluid flows. And what is the reason I got into that is because my friends, the guys who do numerics, told me that within a couple of years, they will be able to reduce the error bars from 10 to the minus 2 to 10 to the minus 4 on these exponents. And that made me very happy because that will distinguish who is right and who is wrong, because there are a couple of other formulas available in the literature. Turns out it's difficult for them to do. And then I thought maybe it's a good idea to try to teach the machine to learn the statistics and give us these numbers. So we started several projects. And the first project was to try to learn how to solve a PDE, to teach them. So this is the paper that is on the archive. Most of the people here are computer scientists. And the question was, I give you a differential equation like that, evolution equation, here's some nonlinear operator. Can the machine learn to solve this? And so typically the way people would try to attack this problem, they would give you initial conditions and some solutions at a finite t. So it's like two images. And then it's like an instance and a label, and then teach it to, by a supervised way, to give you solutions for other new initial conditions. That's the way it's done. Actually, we managed to teach it also to learn the whole path in between, namely to give you all the time steps in between. This plot is not very good. It's about 2D boogers, not Navier-Stokes, but we did started to see the evolution of shocks, etc., in these systems. And the question that actually is very important in this field at the moment is, because these are chaotic systems, how much in time can actually the machine still keep track, because it's very sensitive to initial conditions. So I think there's a lot of potential in that direction. The second thing that we try to do is we try to understand the complexity of the problem of turbulence as viewed from the machine. Okay, so we can train a neural network to distinguish a turbulence fluid from chaotic ones, noise, and images of cats and dogs. And the question was, what is the relative complexity of these various classification tasks? Is it more complicated to distinguish dogs from cats compared to turbulence from chaos? That was one question. The second question was, it was about the depth. So as you go in the depth of the neural network, it starts to see different features at different scales. So the question is, can you analyze the complexity not in general, but at different levels of scales? Maybe certain scales are more important than the others. And the third one was, could we actually understand what it uses? Because the machine at the end of the day tells you this is chaos, this is turbulence, etc. You want to know why. So actually, we managed to answer all these three questions. I'll start from this one. Actually, here it's actually very simple, very tricky, in a sense, simple or tricky. The way you trick the machine is the following. You think that there is a certain quantity, in this case, some 2-point function that you think that the machine is using. What you do is you create a data which has got nothing to do with turbulence, but has exactly this particular 2-point function. And then you ask the machine to tell you whether it's turbulence or not. If it tells you it's turbulence, you know that's what it did. So this is called an adversarial way. So what were the images? So, I mean, if you look at the eye by yourself, you can easily distinguish. I mean, this is like incompressible. These are vortices. So it's vortex structures. And this is incompressible turbulence. This is weakly compressible turbulence. This is chaos, incompressible chaos, compressible chaos. And by the way, chaos, I mean that you didn't reach 10 to the power 3 as Reynolds number, is like 100 or something. So it's chaotic, but it's not fully turbulent. There is no scaling. And this one is noise. If you will look at it by yourself, you can easily distinguish. The question is whether the machine does it well or not. And so introduce a concept that actually, so let's see, yeah. So there's a concept that is introduced in another paper by Umod Yanning and collaborator, something called an effective dimension that actually sort of does a PCA analysis on the data in different stages. And what it does, it tells you the effective complexity of identifying this compared to the other. It's actually, I don't know if it's easy to see, but the cats and dogs is actually very difficult. So what you would think is easy is difficult, while if you will look at chaos and turbulence, it's very easy. So it's counterintuitive. But then the last thing we ask the machine to do is the following. Now produce for us, like we give you pictures of turbulence, produce for us new pictures of turbulence. And the way we know whether it's correct or not, we take those pictures, we read the velocities, and we try to understand whether it gets the right scaling. Let's say Kolmogorov scaling. And it turns out that this is a difficult task. So while machines can easily produce through faces of celebrities, etc., you have to produce a real turbulent picture that you can check by the scaling dimension, it's much more complicated. So this is a task that remains. And so thanks a lot and happy birthday, Hiroshi.
Thank you. Well, thank you very much for your kind work. So this brings back a lot of good memories, and I want to remind you that I paid for the first month's rent in Berkeley.
That's correct. Yes. That's yes.
Yeah, so it was interesting because we all made an offer, and then at some point you sent me a message saying that, well, I don't need dollar, and then for some reason you couldn't bring money or something, and then you asked me to pay for the first month.
You are right.
So,
Yes.
so I talked to Kyoko and said, well, I have some small amount of money left in case like that, and so that worked pretty well. So we should thank Kyoko for
Okay, we should do that.
Anyways, I have one brief question. So for the field theory part,
Wait a minute, did I give you back the money?
yeah, you did. Yeah,
Well, just to make sure. Because with the interest rate, who knows?
that was like 25 years ago. So
Right.
you did.
Okay.
So for the field theory part, so KPZ is for two-dimensional Euclidean
Right.
theory,
Right.
and so you are applying this.
Right. So when you reach a steady state in turbulence, it's
Yes.
Euclidean theory, but it could be in higher dimensions.
Right.
It actually turns out that KPZ is not only in 2 dimensions. We are used to it in 2 dimensions, but the mathematicians think about it in general dimensions. So in general dimension, they give you the following problem. They tell you, oh, there is this scaling dimensions or whatever, fractal dimensions with respect to Euclidean Lebesgue measure. And now they tell us what are these numbers with respect to this new measure, which is e to the gamma phi times that measure. And phi is a low correlated Gaussian free field. And the answer is KPZ.
Oh, I see.
Yeah.
So it's a different derivation.
Yes, it works also in different dimensions. Yes. It's a probabilistic statement.
I see.
But it was really honestly first derived in KPZ.
Right.
The mathematicians came only afterwards.
Thank you very much.
I have two quick questions. To train on a machine learning stuff, to train it, you need a fairly large corpus of training data. An interesting part, of course, is condition with Turbulence. So one question is where you get all this training data, including the condition. And second question is, can you say a few words about various architectures? And I didn't mention it in the talk, but what works with that?
Right. So the first question you need to produce data. For that, you need a student. And that was really a team who did all the numerical. He just solved Navier-Stokes equations and he produced lots of data. And that data, before it reached turbulence, you can use it for chaos. Otherwise, for the architecture, so the architecture for the solution was a hyper network one because we needed to have another network in order to give you these time steps. And the architecture for the complexity just ResNet. It's a very simple supervising.
Maybe you did, but did you incorporate the scaling data structure of the neural network or not?
No. Neural network knows nothing. You just give it images.
But if you want to extract exponents, it would be better to use the scaling in the neural network.
Yeah. So that two possibilities. One possibility, neural networks they allow to learn probability distributions. You give it enough data and they identify the distribution. So one thing you would say, okay, if I give it enough pictures, images of turbulence, it will learn the distribution. It will be able to produce for me new ones. That's what we try. If you try to bring in more information, like for scaling, etc., maybe it will be easier, but then actually there is a prejudice, there's a bias that you're putting in. I think that it is able to learn. It's just that it seems to be much more complicated. So in this machine learning business, there is something called the latent space. Some kind of a space that actually captures the details. Turns out that for faces, etc., doesn't have to be that big. Turns out that for turbulence pictures, if you try to all these intricacies, etc., it has to be much bigger. So we did manage to get pictures that naively we look to you. By the way, you could see in the eye that there is a problem, but if you try to calculate the scaling, it will not give you the right numbers.
Maybe if you improve the scaling in the architecture, it becomes a simpler problem.
It is so there is this question of how do you incorporate the physics that you know inside the architecture to make it like, better. We didn't do it. Maybe this is the right thing at the end of the day to do. I was hoping that actually we just throw it enough data and that it will just be. But actually there is an interesting question. For instance, if I give it a data at a certain resolution, like errors of 10 to the minus 2, will it be able to give me results later which are 10 to the order of 10 to the minus 4, we produce more instances, or actually it will be stuck, namely it will not improve on that? It's a question which I do not know the answer to, and I think nobody knows the answer. It's a question whether these errors have a bias or they will be averaged out or something. I think that there is a chance that it will be able to give you better resolution compared to what you actually gave it in the beginning. Yeah. This trick is known as super resolution. In many companies, they use it in order to improve the pictures that you see. You see all kinds of pictures, and then suddenly you see that they look much better. But I don't know in physics whether it's going to destroy these exponents or whatever. It's much more delicate.